Okay. Right. Hello, everyone. So I'll be on this side. Maybe you cannot see me. Thank you for joining me today. I'm going to present my work that I was doing for my PhD, which is building intelligent monitoring system for human activity recognition. Mainly, we have two systems. One of them is the smart building application, and the other one that's another system that can be used for some IoT applications to that simply to turn a building into a smart building. This work has been done so with many people. You can see that when I started the talk. So an IoT is a term that's very well known to everyone almost these days. Even kids, they know these days about IoT. You can hear like these days about IoT workshop for kids, IoT for kids, something like that. IoT is a new paradigm that is known to, as I said, to many people, in which we build some smart systems or that's equipped with sensors. A very simple example of an IoT device is a sensor that is the motion sensor that we have it in these rooms that in the buildings. So motion sensor will detect the motion and turn on the lights, for example. Now, if I connect this sensor to the internet and let it pull the data to a server and then use this data for something else to get these measurements, play with them, then that's called simply an IoT device. Nowadays, we have a lot of these, thousands of these. Another example of the IoT devices is simply the smartwatch that we have. Any type of smartwatch usually these days is equipped with sensors, and that sensors will collect some measurements. If we just take this data from the smartwatch, send them over the internet to a server or any type of network to a server, then here this is called an IoT device. The smartphone, whatever you think about it, these days it's almost like it could be like turned into an IoT device. The IoT, I forgot to mention, IoT stands for the Internet of Things. So almost everything is connected to the internet. I can connect the fridge, my car, smart car, and everything is connected to the internet. So we are living at this time of the internet and the IoT. So that's why I'm talking about the IoT, because I have two motivations, in fact, for my research. First thing is our society, especially the Western society, is aging, which is a good sign, in fact, that people live longer, and thanks to the advancement in technology. So people nowadays, they for a long time, in fact, some statistics are shown here in this diagram, which is composed like the statistics with 8 years ago. Shows that expect that the number of people that age 85 or 65 or above is going to be more than the number of children, the number of people that is 15 or younger than that. So that by the year of 240 or 250. So, which is a good sign, in fact, but we need to be prepared for that moment. So if you think about the pandemic, and unfortunately what happened during the pandemic, we remember, if you look into the news, we see that these pictures, we saw pictures in which people would go to the emergency, but there is no room for them. There is no bed. There is no enough staff to take care of them. So in fact, why? Because the healthcare system was not prepared for that moment. So now how to be prepared for such a moment in which we are going to have more older people, which are our loved ones, living with us for a longer time. In this case, we are going. So that's one of the motivation where you would like to. Now, so some of these people, unfortunately, will have like some conditions, chronic conditions or other conditions. One of the things that happens to each one of us. When we get sick, we go to the doctor. The doctor is going to write a script and we take the medication, right? We need to take medication on a specific time for a certain amount of a certain number of days. So for people with chronic disease, they need to do that every day, maybe more than one time a day. And they should not skip any dose. They should not. So how to monitor them? How to use this technology to monitor them remotely? In this case, if we do that, we are going to push the load from our health system. In this case, we can monitor them remotely while they are sitting at home. Another important thing, another fact is most of the other people in this part of the world, like to live alone when they get older. They would like to live in their homes or in senior houses usually. So how to monitor them, how to take care of them while they're alone, how to use the technology and harness specifically the IoT and both IoT devices for that goal. That's one of the motivations that I have, and later you'll see that how I connect that to my application, that system that I built. The second motivation is, again, since that these days we have a lot of these devices. Like in this room, you can see like there's an IoT device that's connected to the door. That's which is like the peptide. We call it peptide. Simply to switch sensor that detects the opening and closing of the door and reports the data to someone. I can take this log and see who opened, when the door was opened and closed. I can see the lights and other things using other sensors. So there is an increase in the IoT devices around us. We have at home the Alexa, the Amazon, the assistants, and other things. Each one of them is equipped with a type of sensor that we can use to improve the quality of life. If I can detect what was the activity in that room, maybe I can increase the comfort of the user. Another thing is, and then I will increase the productivity of that person, if that's a workplace, for example, by controlling a fan or turning off the heat or the AC in general, controlling the AC. And if also I can monitor also the person, if he is active, if he is moving, if there is a motion sensor, if there is an accelerometer, all these things can tell me if there is a vibration, for example, in the room. And using some algorithms, some machine learning, we can see if this algorithm, what type of, for example, of activity was there. So that's the other motivation with that, to increase the comfort of the user. Another important thing is the energy consumption. So all these consume a lot of energy, and everyone, almost all countries in the world are now heading towards the green energy or clean energy. In order to save some energy and mitigate or the climate change, all these things. So if I can detect the activity in a building using a device, I can control the energy consumption, minimize the energy consumption in that building, and then we can also help in mitigating the climate change. That's one of the applications as well. So these are the two motivations that behind my research. However, there is an important fact. These devices, so here I have these devices that we built. These devices are useless without the human being, without the human interaction. So in order to collect data, in order to activate the sensors here, I need the user to interact with these devices. I need the user to, or the subject in that building, in that space, to move in that room in which I have these devices. I need the user to take the medication from this pill bottle. Now, the physical interaction of the user depends highly on the design of the system. So that's an important challenge, and that's the main focus of my research, which is having having, for example, two different designs of a pill bottle. What will be the effect of the result? What will be the effect of that on my results? Will I be able to see if the user opened the bottle or not, or who was that person or not? All right. So that's the motivation behind my work. That's a list of more publications that I have. I picked some of them. So the physical interaction in general, I mean, the human with the system interaction happens at two scales mainly. Well, here my focus will be focusing on at two scales. One of them as a personal scale. In this case, the example that I'm going to take, which is the smart pill bottle. I mean, a medication bottle that's used by someone to take medication, and the other one is at the indoor environment scale, which is the other device that I'm going to do. So I picked some of publications. The first system that I'm going to talk about is called the PhD. So PhD tries to target an important problem in the healthcare. That's called medication adherence. Medication adherence is simply defined as the extent to which a patient agrees with a health giver. So when we go to the doctor is going to take this amount of pills, 10, 15, whatever, for 5 days, 3 times a day. So then we should take the medication in the morning. After 8 hours, I take it, and then third one after 8 hours, and so on. And we should finish all the medication. Now, if the person doesn't adhere to the health caregiver, he skips the doses, he doesn't refill the medication, or he doesn't take the medication at all. So that is here we have the problem of medication non-adherence, right? So which is very complicated problem, and that's enabled like a wave of research in this field. In fact, medication adherence problem is important because it causes like a lot. It causes the healthcare system. It causes like the deaths. A lot of people like they expect based on like their health status, and if they take this medication, we expect, for example, that person to live for another 10 years. But if he keeps skipping the dosages or doesn't do the refill and other things, he may die after 5 years. Not 10. So that's called, in fact, the premature death. That's what the term they use. And this costs, as you can see, like $billions for the healthcare system, for the government, and sometimes, unfortunately, may lead to death, especially for people like with chronic disease. You know, like the condition will get worse, and this may cause like more problems, and leads to death. So the medication adherence problem is very complex and important problem, which enabled like a wave of research in this field, and wave of research in which technology-based solutions were proposed. Some of these could be like, for example, vision-based systems. You know, like if you'd like to monitor someone living alone, you can put a camera down in his house or in a specific home, and you keep monitoring that person to see if he is going to take the medication or not, or specific, based on the schedule that was provided. Another thing is by using something that's called proximity sensing. So proximity sensing simply is by attaching a kind of sensor. Here we call it RFID tag to the medication bottle, and you can see that here there is a drawer and there are some medications. So the assumption is if the bottle is within the proximity of the reader, of the RFID reader, this means the user didn't take the medication. Once he removes it from that place, it will not be within the proximity or out of the range of that reader. So we can assume that the user took the medication. Third one is by using wearable sensors. As we said, these days like everything is smart. So we have, for example, smartwatch. We have the Fitbit devices. We have some neck-worn devices that was bought to monitor this activity, which is taking the medication or not. And finally, this smart pill bottles or containers. So there's like some commercial products that we can find these days, which are smart medication containers that will tell you if the user took the medication or not. That can be used to track the medication adherence of the person or not. Smart containers. So, for example, here there is a system with many like compartments, and that was developed, I think, by the group of is on the call from the university. So all these devices are equipped with sensors, and then the aim is to see if the user is adhering to the plan that was provided to him or to her by the caregiver or not. If you are interested, you can see that most of these systems in the review paper that we published in 2018. For us, we focus on developing a smart pill bottle. Why? Because we think that smart pill bottle is more appropriate for the user. For example, if the user wants to travel, it doesn't need to take a whole container with him, or a smartwatch or whatever. I just think that he needs to remember it's just a smart pill bottle in which he has his medication. So it is a mobile device that can be battery equipped, that can be equipped with batteries and sensors. Now, before designing our system, we said, okay, let's see how many sensors we need. What should we do with the sensor, and how to design the pill bottle. So we gave a fake pill bottle to some users, and we asked them to do some experiments. So without putting the sensors there, and you see, I can see here in the video is we noticed something that first we started that our aim is to develop a system that detects the opening and the closing of the bottle using some sensor. If we detect opening and closing, measure the weights of the compartment and see if there's a difference. And by doing that, we can see that we can assume that the user took something from the compartment. Now, we noticed something else here, which is very interesting. We noticed that each one of the user has its own signature in taking the medication. So, in fact, what we want to do is trying to identify the user as well. So now, in addition to finding if the user is adhering to the medication, we'd like to see if the user is the actual user or someone else. So you can see that the most important parts. Again, that's another set of experiments that we did, and you can see that each user has its own weight, its own signature in retrieving the medication from the compartments. Like you see, like one of them is on to the right, other one to the left, and Joseph was sitting here did it in a very nice way. I mean, he didn't tilt it, he put his fingers like this. So it has he has its own signature and taking the medication. So which makes our work unique is the fact that we developed a smart full bottle system that helps in identifying the user or the patient or the person who was trying to take them to retrieve the medication from the full bottle. One important application of this is definitely medication adherence. This means that if I can identify that person who took the medication, this means that he is adherent or not. And another important thing is the drug abuse monitoring. So, I'm living out in my apartment with my kids. I would like to see if maybe at some point we have someone trying to take the medication, not the actual one. I mean, and that's that's the problem is called the drug abuse problem. So by doing that, we can enable this application, medication adherence and drug abuse monitoring. So we see that here, and going back, sorry, to these slides, we can see that we have two important parts. One of them is the caps, so which is the thing that we open. There are different types, definitely, of the caps and the compartment, because the user will we expect the user to pick up the bottle and shake it out to retrieve the pill. So what we did is we put two sensors, one in the cap, as you can see here, and the other one is in the compartment, and both of them are battery powered. These are because we think these are the important parts in the system. And again, if we capture the sensor using these sensors, we'll be able to identify the user, and that applies almost to everything that we do in our life. I mean, the way that I drive is different from my wife's way to drive, and the way I write is different from my son's. So each one has one signature. Our system is made simply of two accelerometers. So we put a wireless transmitter that we call PipTag, and this system is developed here in Murtadha by previous students, and we equipped it just with one accelerometer. So our system is simple. Usually, other system more than one sensor. They use accelerometer, gyroscope, and magnetometer, but this is unfortunately consumes a lot of energy. So in our case, we use just a digital accelerometer to minimize the energy consumption, because we'd like to build a practical system that can be used by the user for a long time. And we equipped the cap with one sensor and the compartment with another sensor. This can be powered by two types of battery: lithium battery or coin cell battery. Coin cell battery will last for almost a week, given that we do sampling 10 times a second. And the system will do the transmissions 10 times a second. We can improve that by adding more sensors, for example, pressure sensor. However, we didn't do that, but I mean, that's also possible. Right? We can improve that. Half AA lithium battery will make the system last for 30 years. The patient sense pipeline, the patient sense system is made of two components. The hardware, as I showed you here. That's one of the pill bottles that we have built. We have other pill bottles as well, and the software. So the software component now, one of the aims is to get the data from the system. Once I have the data, I can take this data and then process it, and then see if the user is taking the medication, and see if the user is the actual user or someone else. So our pipeline, this pipeline is called the machine learning pipeline. We have multiple components here. So of course we collect data from some users, and we did experiments with 16 subjects. do the experiments like 10 times, and once we get the data, the type of data that we're going for time series data, simply like curves like this, which is like from the accelerometer, we have X, Y, and Z, and we do some cleaning for the data. So in the part of machine learning, the data sometimes is noisy. Not all of data is interesting for us. So what we do is we clean the data, remove some parts of the data, and then what we do is we in fact extract the pulses, extract the wiggles that results from this activity, which is like opening the cap, shaking it a little bit, bending it back. And these are the wiggles, as you can see here. The small wiggles that's generated from this activity. So we take them, we put them in a bag of pulses, you can call them. And what we do then is we do another phase that's called the feature extraction. So now we would like to, in order to train the system, we need to extract some features. This extracted in a given way before we do provide them to an algorithm to do the classification. I think in this slide I'm describing these steps in details. So these are the wiggles, as you can see to the right. We put them in a bag. What we do next is we measure the distances between them by using a technique that's called DTW, or dynamic time working, in order to generate the feature. This phase is called the feature engineering. The labels here, the ultimate aim is to label these pulses. What we do is we put them in we measure the distances between them using the TDW, and we create a distance matrix. Next is we take this distance matrix and we cluster all the distances that we have. So simply these distances that are close to each other, they will fall in one cluster. Now, what we do next is we give labels for each one of these clusters, cluster 1, 2, up to n. And then we take these labels that we gave to the clusters and label the wiggles that we have. So then at the end, we'll end up having a labeled wiggles, as you can see here. And each one of these, like here, we have two activities as two, because you can see like two red boxes. So these are two activities. Each one of them corresponds to one medication taking activity. And here we have the labeled in this case, and this will be our features, and they correspond to one of the users when that user is taking the medication. We take the feature or the labels that of these wiggles from the compartment sensor and from the cap sensor, put them together, and it will be our features. So that's how we create our feature matrix. Next is train the system and then do the classification. We did this experiment because, as we said, with 16 adults, and they did the experiments 10 times. The first thing is that we'd like to see what's the effect of increasing the number of subjects. Imagine that we have a family. What's that family size, and what's the effect of increasing the number of subjects on the family size, or in that family size on the accuracy of the system. Because we'd like to see if the system is able to identify the user correctly or not. Here we did it in two different ways. One of them is the binary classification by using a technique that's called the binary SVM. Simply here we split the data into two parts. In the one of the parts, we are focusing on the actual the user. So the kind of answer that we are going to get from this algorithm is yes or no. The person A take the medication or not, because it is binary classification. So something like creating a line between two groups. The accuracy, as you can see here, like using in a group or in a family of three, you can identify if that was the actual person taking the medication or not, with an accuracy of over 90%. As the number of subjects increase in the family, then the accuracy is going to decrease, and that's it. I mentioned that I focused on this number, like family of three, because the average family size in the United States these days is less than 2.6. So still, like our system for 16 subjects accuracy is achievable accuracy was around 85%. So that's for one versus all SPM or for binary classification. We also did multi-class classification using other techniques. Multi-class SPM, random forest, and the k-nearest neighbor. these are very well-known machine learning techniques, and that can be used for the classification. We also see like the accuracy. In fact, when the number of subjects is 16, the accuracy will be less than 84%. So in the previous case, we had 85% in fact for 60 subjects, but here it's more. Why? Because in multi-class classification, the system is going to give us the actual ID of the person. Who was that person that has interacted with the system? The previous one will tell us if it was the actual person or not. If it is not, we don't know who that was that person. But here it will tell us if it's user 1, 2, 3, or whoever that took the medication. Also, we looked into the accuracies from one of these sensors to see if one sensor is enough, of the one in the cap or the one in the compartment. We using the bottle sensor, like using the one inside the compartment, the accuracy was a little bit over 80%. So it's not that bad. I mean, in this case, if we use one sensor, this means that we can reduce the cost of the system. So I have more results, but due to the short time, I picked all these results. However, in the publications, we have all the four results, and same thing in the thesis. So 3 takeaways from patients. These systems like the SPM, Kenios, Neighbor, and Wonderful are called shower models. These are simple or basic models. So they are efficient, they are lightweight, so we can run them very fast and get the results. But they need feature engineering. They need that's why what we did is we created this pipeline to extract the features and label the wiggles, and in order to create our features. And they are suitable to tell us if that was the actual person or not. Well, in the case of trying to identify the actual person, the accuracy was not high, and that's expected because that's what we paid for. I mean, that's the basic model that can run for it's very light. Like it doesn't take that much computation.
Do these models include time? You have DTW in there, but you have a series of features.
Correct.
You also look at the rate at which the feature is expressed.
You mean like how long it took for that
slow or fast?
Not really. Well, so the DTW is going to take like each two of these pulses and measure the distance between them.
Right, but you count the stretching you have to do.
Yeah, but correct, but the DTW is going to take care of that because DTW is going to compare one point to multiple. I have backup slides. I can show them later. So it shows that it compares one point from one of these from the shorter pulse. So imagine that we have two pulses. One of them is short and the other one is long, and they were produced by. They are similar because they were produced by the same person, right? That's what you mean, Professor. But you're right. Like here we have the multiple data points, but here we only have like a few. So the DTW is going to it's going to compare one point from the short one with multiple points from the long one. So that's why we picked the DTW. Otherwise, they will have other distance measures that we can use. I have some backup slides. So I can show them in diagram later. So that's the takeaway from patients. Will tell us someplace if that user is efficient when tell us if the user was the actual user or not. If it's not, then who was that user? It's not really that's efficient. So we are next is we are tackling another problem. Given that the user is taking more than one medication. So when you go to the pharmacy now, we imagine that someone goes to the pharmacy and they will give them a new medication. They will give them a new medication, maybe in a different pill bottle or in a bottle that has a different shape from the one that we have. I imagine like a multivitamin and Tylenol 1. You know, they're different in size, shape. So, and we conducted again experiments, and you can see here that's the same user doing the experiments, interacting with two different pill bottles, different in the shape or in the physical design. And we can see the effect of that because the first one was like taking the car, put it there. I mean, just it is not a turnable, like the yellow one, it's not like it's a clickable car. You can imagine like this. The other one is not a turnable one that it should be turned. So this affected the way the user interacted with the system. I mean, the design had that effect on the way of the physical interaction between the system between the human and the system. So what is the effect of that in case that we have more than one system? And that applies to any kind of smart system, whether it's smartwatch, whether it's or a pill bottle or any other example that or any smart system that could with sensor. So the scenario of having like in this case two compatible sensing systems, but they are different in shape, they're different in the physical design. What was the effect of that? Here we are trying to tackle like few problems. The changes, as we saw like from the previous video, the changes to the bottle design will require, in this case, retraining. Because if I train the system and do classification and have it like the system ready to classify new data by using this yellow pill bottle, which has this shape, I'll not be able to use the same bottle, the same model to predict new data from the white pill bottle. Why? Because it was different, and the user interacted with this with this system in a different way. So this will affect the data, will affect, and the result is not going to be good in this case. The other thing is what we saw, as we saw before, like when the number of subjects increase, then the accuracy will decrease. So how to fix this problem? We need more. That's why we use investigated other machine learning techniques, as you can see later. The third problem is, what if we have small data? In fact, we conducted new experiments during the pandemic, so we didn't have enough users. Only had 10 subjects, and then so we had the problem of having small data. So how to deal with this situation also? These are the three main problems that we'd like to tackle in a system that we call it is that view again. So here, what we do is we apply again some machine learning techniques. First, we built two pill bottle systems, as you can see here. They are different in shape, but they are equipped with the same type of sensors. And we applied some techniques, mainly three techniques. First one is domain adaptation, in order to reduce the number of labeled data from the new pill bottle that's required from the new pill bottle in order to predict the user. So which is applied in this case across two domains. Each one of the domains is one of the pill bottles. The domains here we call later they are going to call it the source and the target. So the source is the yellow one, while the target is the white one. What we'd like to do is we'd like to take the data that we have from the yellow one and only the data from the new one, and then predict data from that's data that's coming from the new one. So that's they call domain adaptation. Second one is domain casting, by taking the time series data that we have, the wiggles that that's what generated from the medication taking activity. We converted them in fact into images using a technique that's called recurrence plots. Recurrence plots, as you can see later, you will see later, it is a textile images that represent that's good in representing the actual activity. Why we'd like to do that? Because we'd like to use deep learning models. So deep learning models do very well when it comes to the images. And if we take a deep learning model that's trained on a very large data set, we can apply transparent learning in this case. So these are the three main techniques that we use in order to handle this issue. So we collected data, as you can see here. In fact, this is a system that we Justin helped with this, and Joseph as well. And we developed a human computer interaction system that helped to collect the data. And we did some experiments with 10 subjects, as we said, because we did that during the pandemic. We took this data, we converted them from time series data to images, as you can see here. So these are the images, and we, using some algorithms, we can generate these images that are called recurrence plots. These are textual images that represent the activity in a very good way. So you can see here on the top left, these images represent two activities that were conducted by the same subject. Subject 1, same thing here. Subject 2. So they are very similar to each other because they were being done by the same person. And you can see here if the user does the activity in a different way, so the shape is going to change. Okay, so that's the why we use the recurrence plots. And next is we took this data and we fed them to a deep learning, mainly that's different types of CNNs. So what we do here in this pipeline is we combine all these techniques together: transfer learning, domain adaptation, and the domain clustering. So the data first is going to be converted, as you can see here, from raw data to the time series data to images, and then here we split the data into 2 domains. The first one on the top is the data comes from the yellow bottle, while this one is coming from the white bottle. So one of them is the source, and the one is target. And then what we do is take all the data from the source or from the yellow bottle and some data from the white one and use that for the training. Now, when it comes to the target one or the white one, what we do is we try to increase the number of samples by using data augmentation, by generating more fake samples that are similar to the original ones, in order to make force the deep learner to focus on these new samples. And next is we took and we saved some definitely for the prediction. These are labeled data. And what we do next is to do transfer learning. So what we did is we took a pre-trained CNN model and we used that for the prediction. Different techniques, VGT, mobile data, and other. So we can see here in this diagram, in this plot, in fact, that we can achieve a higher accuracy for 10 subjects. Before that, we didn't get this amount of accuracy. So it's close to it is 90% in fact for 10 subjects. If we compare that with the same pipeline, so if we take this pipeline, this same pipeline, but replace, but we keep that only the time series data. And replace the CNN with shallow models that we used before. We can see that still we cannot achieve this accuracy. So using CNN definitely will give us more accuracy. And that's what you can see on this side. So as we increase the number of labeled target data that's coming from the white bottle, the accuracy is going to go up. And we can see the comparison with the shallow models on the right side. So for 10 subjects, the accuracy is going to be around 60 to 70%, while here we can achieve 90%. So that's the power of CNN. So the takeaway is that both of the, and we can see that definitely the design of the system will affect the physical interaction with the system. Using transfer learning was very helpful in increasing the accuracy of the system. Also using the CNNs as we can say, it's better than the shallow models, and it will increase the accuracy of finding the actual person or not. Because if the shallow models did well in the previous study, when telling if the user was that user or not, while here we can separate the users and find the actual user that interacted with the system. Third important problem is called non-compliance, which is having a person that doesn't agree with the doctor and will not take the medication. For example, what if we have a person that's trying to fool the system? So that person knows that this system is smart, so to check the opening and the closing, see if the medication was taken or not. So imagine that he will take the pill bottle and plays with it, shake it, and that's it. And open it and shake it and just to fool the system. So we use the same pipeline, in fact, but here we change it to compliance or non-compliance. We have 2 classes, and you can select all the details. Here, we did some experiments, and again, the results was promising. 87% to tell if the user was really trying to take the medication or just shaking or playing or following this. We took only like a few cases, 3 cases, like moving it to the right, to the left, up and down, but we can take more cases. So there is a problem, which is a very complex problem, in fact, because as we said, there is this very complex problem, and that depends on the personality of the patient. So what if the user took the medication but didn't swallow that pill, or didn't take it, ingested that? So how to monitor it? There has been some that work. In fact, for example, adjustable biosensors. So adjustable biosensors means that sensors are equipped with something very like small circuit, and using some like kind of pills or band they can attach to the belly of that person. We can see if the pill reached to the stomach or not. Now this is very invasive because it's some electronics there. Also, there has been some work about in which wearables were used, including neck wall sensor. Now, neck wall sensor imagines someone wearing like this neck wall thing in order to detect if he's chewing or swallowing. That's very invasive again. There has been now some advancements in building the earbuds. So earbuds are the headphones that's used. And nowadays they are equipped with sensors, with motion sensors, with proximity sensors, in addition to the microphone. All right. So what we focus on is, in fact, there's a group at Illinois University, I think, University of Illinois, that they do all these things. What we did is we reached out to company, to Nokia Labs in the UK, and they provided us with a special earbuds. So that's called the Pieces. So these are special earbuds that are developed for research only. And this report with the number of sensors, motion sensors, gyroscope, proximity sensor, in addition to working as an earbuds. What we did is, these days, almost a lot of, especially young people, will wear these all the time. So, and given that, what we want to do is we wanted to see if the user what the user is doing, if he's moving like his head or speaking or chewing or drinking something. That's based on the claim that is medication taking activity involves the swallowing, and this point of the face is at which like the low jaw is connected to the skull. So by moving like this part, this is going to cause some pressure in the ear canal that can be captured by earbuds, by something in the ear. So here we use the earbuds, and we did some data. We did some filtering for the data. We did some feature extraction by just simply extracting some statistical measurements, some statistical features, and we did some activity classification in which we'd like to see if the person is drinking a sip of water after swallowing the pill, for example, speaking, or just chewing, or at least mainly, I think, 5 activities. We did some experiments, and the results were was they asked if we're using the leave one subject out accuracy for the leave one subject out approach. The accuracy was like around 84%, and it tells us if the user is swallowing or not, for example. Now, if we'd like to find the actual activity, chewing, swallowing, or speaking, the accuracy was around 80%. Also, we said that what's the importance of the sensors? Can we use gyroscope only or not, or accelerometer only, or both of them? So in the previous experiments, we did that by using gyroscope and accelerometer, and these are the results. So we see that definitely the highest results achievable by using both sensors. So we can achieve the takeaway from this part of the thesis is we can detect the point of the person, see what's the activity that's done by the person. However, as we said, medication adherence is very complex problem. It cannot be solved by using only one technique. That's the main takeout. So we think by taking a combination of this, for example, if we take the smartphone bottle and kind of wearable, for example, the earbuds, we can detect if the user opened the cap, closed it, shaked it, who was that person, retrieved the pill or not, and next, if that person swallowed the pill or not. So, there's another question. I'm going to switch the gears a little bit. So I'm going to talk about the other part of the thesis, which is the physical intelligence, monitoring the physical intelligence at a different scale, at the indoor environment scale. Here why sensing the human activity? So that was one of the problems we tackled is the medication adherence, which is very important in the healthcare sector. And next is if we can monitor the activity of the user in any environment, as we said before, we can enable some applications. We can tell the person that you moved that number of steps, you watched the TV that number of hours or minutes. The light was on at that time in your room. All these things. What's the and then so we can enable a number of applications, and maybe also can increase the comfort of the user. So it's not that easy. There are some challenges when deploying such systems. Now the other one is this one, the right one. So it's called the Maestro, which is an IoT node with a number of sensors that we designed for this specific purpose. So to monitor the human activities in the building, we can ask the user to wear like a device all the time, even while he's taking a shower, or even while he's sleeping, or be within the proximity or within the vicinity of a camera in that room in order to capture all of these activities. And then based on the data, we can identify if the user what the user did and provide like the result to the user. So these are intrusive, because we ask the user to use specific smartwatch or specific device, or be within the proximity of a camera, all this. So we have the privacy issues here. Human activities in the buildings, in fact, varies, and you can see we have different. If you think about it, we have different activities that are done, and so and each user will do this activity in a given way. In order to study the human activities in the buildings, what we did is we built a system that's called Maestro. So Maestro is a system that equips 9 sensors, 18 sensing channels. That's the circuit, that's the board that we developed with the help of Joseph and Professor Howard. So what we did is the ultimate aim is to enable some applications, and also we can develop a test bed that enables that's made of some Maestro units that will enable us to enable more IoT applications and tackle some problems in the IoT field. So, for example, occupancy counting, user identification, and activity recognition as well. The data it's sent to a server. So Justin Dink also helped in this work. So what we did is we have some data. That is sent to a server. Under the server, we plot the data, display them in real time. In fact, that's the video that shows that. I'm not going to play it. The data will come in real time to the server, shown in real time. We did some use cases by using Maestro to show that Maestro is sufficient for this problem. First thing is we developed a number of sensors. I think 2 of them in an apartment, and there were family of 5 in that apartment. We'd like to see what was the changes in the occupancy in that room, what happened in that room, what activities, and how many people are, for example, in that room. So you can see and the accuracies were very good by using a lot of models. So we can see we have some results for activity recognition, and the number of activities. I think it was 3 or 4, between 3 or 5, if I remember correctly. So the accuracies were very high. Occupancy counting how many people are present within the proximity of the sensor were also good, and that's without using that's by using the data and all labeled data. Now we tackled another problem that's very important. That's active learning. Imagine that we have a lot of data, but labeling is not. We don't have enough labels for this data. So in this case, we use an algorithm, machine learning algorithm that's called active learning, in order to query the user or ask the user for more labels. And what's the effect of that? And we saw that the activity, the results went up as we increased the number as we asked the user for more labels. The second use case is by developing a test bed of the user and developing a privacy preservation and technique in smart spaces. This work is done with tongue. So we did some experiments on 3 users. They did some experiments like typing on keyboard, having a call, writing on a whiteboard. What we want to do is we would like to enable this, so classify these activities in order to provide some IT applications for the user while hiding the identity. If we do that, we can maintain the privacy of the user, because the user doesn't want his identity to be revealed. It doesn't want this information to be sent over the internet. He only wants the system to tell him what he was doing that time, for example, for how many minutes he had that Zoom call or that phone call, all these things. So we developed a GAN-based model that helps in injecting noise to the data, which will hide the identity of the user while classifying the activities done by the user. So accuracies were the results were promising. On the left, you can see that the fusion matrix that will identify the actual user, while on the right one, the system was confused about identifying the identity of the user. So here you can see that across diagonal, the accuracies were kind of low, which is a good indication that the system was able to hide the identity of the user while arraying the activities, for example, activity counting, activity recognition, that space. The last piece is, so still have some challenges, and in fact, the last piece is we are challenging a work that's done by another group, so which refers to a term that's called general purpose sensing. General purpose sensing is very promising. It's very promising term, a very promising topic that we hear about like these days, which stands for just creating one sensor like this and putting it anywhere in the room, and then collect data, and from that data can infer the activities in that. For us, we don't think it's that easy, because if we change the carpet in this room, this may affect the reading of the sensor, one of the sensors. What if I move the furniture? What if I have 10 people rather than 3? All these things will have an effect on the reading and on the physical properties of the signal that's collected by the sensor. So the third piece of work in which everyone sitting in this room, Joseph, Justin, Tahia, she's not here, worked with me on this. We published a paper or a work that's called "Is General Purpose Sensing a Pipe Dream?" So we think that the deployment of this has an effect on the results. The activity itself, how far the activity or that anchor point or the point of event or activity from the sensor, and what's the activity itself, and what type of sensors we have. So all these things, all these challenges need to be addressed. So we did this systemic study in which we did some experiments on the, you can see all the events here. We developed a sample deep learning model on the network, which is a LeanNet inspired CNN network, and in order to extract features from the data that we collect from our test bed. The first thing is we'd like to see what if there is an association between the sensor and the activation and the events that we are monitoring. Here in the heat map, we report the energy distribution across the sensors. We use the energy measure of the difference of the energy measure from the average. So we can see like there is some association between some of the sensors, for example, right, and some of the activities. For example, when we run the filter and the neural machine, we see that the light intensity was the one that has more energy, will tell us more about that event. Why? Because that sensor, Maestro 1, was very close to the event. While if we move to the right, so the Maestro 2 and Maestro 3 were a little bit far from the event. What's the effect of that? Definitely, we don't see that the same thing. So that's one of the takeaway. Each one of the point the position of the sensor is important with respect to the anchor point or to the point of event. The second one is what about each one of these sensors? Definitely, each one of these units, each one of the Maestro units is going to classify the activity with some accuracy, because each one of them will collect the data from the environment, so they by itself it will work. Okay, but if we again move to for some selected event, for example, microwave food processor, I think like B, C, and I, we can see that the accuracy will go down, or it will be different as we move to the right. Why? Because again, Maestro 2, I think, we're a little bit farther from far from the point of the event or the anchor point. The impact of what about the impact of the different sensors on the event recognition? So in this case, we report here the recall or the visual accuracy or the actual accuracy by that specific sensor. For example, the magnetometer, the accelerometer, the audio, and what will be the accuracy of that sensor on that activity. So here we can see this heat map. Can use like some of, for example, like temperature. Tell me like the coffee maker is on here with an accuracy of 100%. First one is very close. Now we may not need the other sensors. That may affect the accuracy itself. If we move to the right, this could be a different. It depends on the positioning of the sensor. It depends on the activity itself. So all these things. I think the last thing is what's the sensor contribution to the classification of performance. What do I mean by sensor contribution? So the previous one, we showed that the individual accuracy for each one of the boxes or the units. While here, what about each one of the sensors that we have in each one of these units? For example, so here in each one is we add one sensor we add like the data from one of these sensors to the rest and see like what will happen to the results or to the classification performance. So you can see that, for example, we add like sometimes we can it's going to go up and up to like for the motion sensor with respect to Maestro 1. With respect to the Maestro 2, the same thing, but the accuracy overall accuracy was a little bit lower. And same thing here, it's out of 1, here it's out of 1.2. So it's not big. So the takeaway here, there's a relationship between sensor type, placement of the event, and the actual activity, and how will which one of the sensors is going to activate and capture that event. There is some association between certain sensors and the classifier ability to classify that specific event. Still, but for general purpose sensing is important, is very good technique, it's very good research topic, but still they need more investigation. And what we believe is having distributed general purpose sensing, not only one sensor, because if I move that sensor to another room, to another part, if I move it to another room, it will tell me something else. We will not be able to achieve all these the same results. For the future work, we think that we can use the smartphone bottles to monitor other health conditions, for example, Parkinson's disease. In this case, if we have a person that's with this medical condition, we can ask him to take the medication from this system while he's at home. Since we have sensors there, like continuously monitor the progress of his condition without asking that person to go to a specific clinic or so. We'd like to definitely to do a clinical study, a trial or study in order to keep that. Developing or modifying this full bottle to be a single point of care, such that we add more sensors, temperature sensor, pulse oximeter, and other things. So by doing that, we can collect more data about the more vital data in this case about the user. And closing the gap in education, as we said, it's very complex and needs to, in some cases, in order to fix this problem or solve this problem, I think we need to incorporate more than one system or one system. With respect to the IoT device that we have, Maestro, and we are developing an IoT testbed that can be used for IoT applications and collecting IoT data, labeled IoT data. So that's what we are doing right these days. We have a robot, we have a positioning system, we have 50 units of these Maestro that we built. Before I end this talk, I think I should thank everyone in this room. Thank you for attending. Thank you for everyone who joined online. That means a lot to me. This work wasn't. I will not be able to do all this work without the collaborating and the help from people, especially Professor Rich Martin, Professor Ortiz, Professor Rich Howard, and all my colleagues, Tahia, Tong, Justice, Joseph, and my friends definitely. Especially, I'd like to thank Professor Martin. He has always like has his doors open for me. Professor Ortiz, I learned a lot from him. I enjoyed attending all the meetings, working with him as a TA, as a PhD student, and definitely my mentor, Professor Rich Howard, who taught me almost everything from soldering to reading data sheets, from everything. I appreciate all these things. Thank you so much, and I hope you have